Here's a vector B in space and a line through the origin along vector A. What point on this line sits closest to B? Let's slide a candidate point along the line. Too far, the distance grows. Too short, still not optimal. Right here, where the gap forms a perfect right angle with the line, the distance hits its minimum. One perpendicularity condition is all we need. That single constraint gives us the answer, and an entire matrix. This is the key idea behind deriving the projection matrix. Let's name the players. Vector B is what we're projecting. Vector A defines the line direction. The projection P is the closest point on the line to B, and the error E equals B minus P. That's the vector from the tip of P to the tip of B. Since P lies on the line through A, we can write P equals x hat times A for some scalar x hat. X hat tells us how many copies of A to walk along the line. So the entire problem reduces to one unknown. Find x hat. Here's the key geometric constraint. The error E must be perpendicular to the line direction A. In dot product language, A transpose times E equals 0. Since E equals B minus x hat times A, we substitute and write A transpose times the quantity B minus x hat A equals 0. Now distribute the dot product. A transpose B minus x hat times A transpose A equals 0. Now let's solve for x hat. Move the second term to the right side. X hat times A transpose A equals A transpose B. Finally, divide both sides by A transpose A. X hat equals A transpose B over A transpose A. Look at what we have. The numerator A transpose B is a dot product. That's a scalar. The denominator A transpose A is also a dot product, another scalar. So x hat is simply a scalar divided by a scalar. One perpendicularity condition gave us one equation in one unknown with one clean answer. The entire projection fell out of a single right angle. Now substitute x hat back into P equals x hat times A. The projection vector P equals A times A transpose B over A transpose A. Let's run a concrete example to see this in action. Take A equals the column vector 1, 2, 3, and B equals the column vector 2, 1, 0. First, compute A transpose B. 1 times 2 plus 2 times 1 plus 3 times 0 equals 2 plus 2 plus 0, which equals 4. Next, compute A transpose A. 1 squared plus 2 squared plus 3 squared equals 1 plus 4 plus 9, which equals 14. So x hat equals 4 over 14, which simplifies to 2/7. Finally, the projection is P equals 2/7 times the vector 1, 2, 3, giving us the vector 2/7, 4/7, 6/7. Let's run two quick sanity checks on our projection formula. First, what happens when we double B? Replace B with 2B, which gives us the vector 4, 2, 0. Now A transpose times 2B equals 8, which is double the original value of 4. A transpose A stays at 14 since A hasn't changed. So x hat becomes 8 over 14, which is 4/7, exactly double the original 2/7. That means the projection P also doubles. And this makes geometric sense. A longer input vector casts a longer shadow onto the line. Second, what happens when we replace A with 2A? The line through the origin doesn't change since 2A points in the same direction as A. Let's trace through the formula. 2A transpose B gives us 2 times 4, which is 8. 2A transpose times 2A gives us 4 times 14, which is 56. And the projection vector is 2A times 8 divided by 56. The extra factors of 2 in the numerator and the denominator cancel completely, and P stays exactly where it was. The projection depends on the direction of A, not its magnitude. We have the projection formula. Now we can pull B out and expose the matrix. Start with P equals A times A transpose B over A transpose A. Now reparenthesize P equals the quantity A transpose over A transpose A times B. That bracketed term is a matrix, capital P, so capital P equals A transpose over A transpose A. This is the projection matrix. Here is what is crucial. A times A transpose is an outer product, a column times a row, with A equals 1, 2, 3, that is a 3 by 1 times a 1 by 3, giving a 3 by 3 matrix, 1, 2, 3 in the first row, 2, 4, 6 in the second row, 3, 6, 9 in the third row. Notice that every column is a multiple of A. This is a rank 1 matrix, meaning its column space is one-dimensional, exactly the line we are projecting onto. Meanwhile, A transpose A is an inner product, 1 plus 4 plus 9 equals 14, just a scalar. So capital P equals 114 times that matrix. This projection matrix has two remarkable properties. Let's look at the first one, symmetry. We want to show that P transpose equals P. Start by taking the transpose of P. P transpose equals the transpose of AA transpose over A transpose A. Now the transpose of a fraction where the denominator is a scalar just means we transpose the numerator. So this equals the transpose of AA transpose divided by the transpose of A transpose A. Here's the key insight. The transpose of AA transpose is just AA transpose again. The outer product of a vector with itself is always symmetric, and the denominator, A transpose A, is just a scalar, so it's completely unchanged by transposition. Putting it all together, P transpose equals AA transpose over A transpose A, which is exactly P. So P transpose equals P, confirming symmetry. You can verify this with our numerical matrix. The entries of 114 times the matrix with rows 1, 2, 3, 2, 4, 6, 3, 6, 9 read the same across the diagonal. For instance, the entry in row 1, column 2 is 2, and the entry in row 2, column 1 is also 2. The same holds for every pair of off-diagonal entries. Second property, idempotency. A matrix is idempotent when applying it twice gives the same result as applying it once. Let's compute P squared. P times P equals A transpose over A transpose A, multiplied by AA transpose over A transpose A. In the numerator, we get A, then the middle product A transpose times A, that's just a scalar, and then A transpose. So the numerator becomes A transpose A times AA transpose. The denominator is A transpose A, quantity squared. Now, one factor of A transpose A cancels from the top and bottom, leaving us with AA transpose over A transpose A, and that is just P again. So P squared equals P. We can verify this numerically by checking the 1, 1 entry. It equals 1 over 14 squared times the sum, 1 times 1 plus 2 times 2 plus 3 times 3, which gives 14 over 196, and then that simplifies to 1 over 14. That matches the 1, 1 entry of P. Geometrically, this makes perfect sense. When you project B onto the line, you get P, which is already on the line. If you project P again, it doesn't move. It stays right where it is. The shadow of a shadow is the shadow itself. Let's step back and see the full picture of what happened. We started with one geometric question, find the closest point on the line, and one constraint, perpendicularity. That single right angle condition gave us a scalar formula. X hat equals A transpose B over A transpose A. When we substituted back, it revealed the projection vector P equals A times the quantity A transpose B over A transpose A. Rearranging that expression exposed the projection matrix capital P equals A transpose over A transpose A. That matrix carries two algebraic fingerprints. First, P transpose equals P, meaning it is symmetric. Second, P squared equals P, meaning it is idempotent. These are not coincidences. They characterize all orthogonal projection matrices in any dimension. Looking ahead, when we move to projecting onto planes or higher dimensional subspaces, the formula generalizes to capital P equals capital A times the quantity capital A transpose capital A inverse times capital A transpose. but symmetry and idempotency will still hold. One right angle gave us a scalar, then a matrix, and the matrix algebraic DNA travels with us from here forward.